Swayam Prabha. Digital India. Educated India.
So, welcome to this session on hardware security. So, this is a 3-hour class and for today, and tomorrow we have another planned 3-hour session. So, before I start, I would just like to make an initial context. I think you have been studying about cryptography, security, and in general understanding the principles behind these subjects. Today what I would like to talk about in this context of hardware security is some of the issues that can emerge when you would like to implement these crypto algorithms. Okay? Because you know that at the end of the day, if you have an engineering pursuit, right, you would like to implement crypto systems on platforms which could be either software, hardware, embedded systems, firmware, and so on. Okay? But often it happens that that when you build a house, right, and you want to secure your house, the thief never comes through the strongest path, right? It often comes through the weakest channel. So what we will try to see, like in this class, or maybe these sessions, is some of the opportunities that maybe hardware designs or in general embedded designs offered to attackers, which the attackers can exploit, and without really solving the hard problems, can break crypto systems. Okay? So largely this class of analysis is what are called as side channel analysis or side channel attacks. Okay? So as you can see by the name, it means that it doesn't talk about the inputs which are the plain text to a cipher and the output which is the cipher text, but still along with these, right, gets or captures some information which we called as side channel information and uses it to efficiently obtain the key. Okay? So when I say efficiently, it means in practical terms actually. Okay? So really speaking that you can demonstrate on real life systems. Okay? So so with this background, let's start. Okay? So I will start with few backgrounds about what are side channels, okay, and just take a quick look at some of the historical aspects of this. But largely, I will be trying to talk about two power analysis techniques. So power analysis, I will elaborate what it means. Very simply put, it means that, so that's the side channel. Okay. So if you would like to implement a crypto system on maybe a mobile phone, okay, or maybe on some credit card, when the crypto operates, okay, it consumes power, right? Any computation will consume some amount of power, okay? But the very interesting fact that we will try to understand in today's discourse is that power consumption has a signature of the secret key, okay? And if you know techniques, then you can utilize that power consumption to do a cryptanalysis which can give you the key, which can give you the secret key. Okay? So this leads us to some statistical techniques, and some of the most commonly known side channel techniques are what we will start with, which are called as difference of mean and correlation power attacks. And then we will try to see how do you implement them. Okay? So in the implementation part, of course, I will not drag you right now to the lab and show you how exactly to capture the power, but rather we will try to simulate a lot of things and from there understand the algorithm of doing such kind of attacks. Okay? So largely this is the plan. So to start with, what are side channels? Okay? So side channels are basically, okay, by the way, if there are any questions, please feel free to interrupt and ask, okay, because if you ask questions, then I also get a feedback about how, or what is the exact communication that is happening, okay. So what are side channels? So side channels are basically covert channels or secret channels which leak information which the designers of the crypto algorithms did not consider. So when you design a cipher, like probably you have studied about block ciphers, okay, and this is largely what I will be like concentrating on in today's discussion. So in a block cipher, you have an input which is called as the plain text. You take a block of the plain text, you apply a secret key. Okay, so typically if you talk about AES or the advanced encryption standard, then you have a 128-bit input, say if I talk about AES 128, and you have a 128-bit secret key. Okay, and you do some kind of transformation to generate what is called as a ciphertext. Okay, and the ciphertext is also a 128-bit data. So it's a bijective map from 128 bits to 128 bits. So by the principle of Kharshkov, we know that the algorithm is known. The algorithm is there in the public domain, and what we don't know is the secret key, right? So now the big question is, if I give you like ample amount of plain text and ciphertexts, can you get the key? So it turns out that AES, being a very well designed algorithm, it has resisted like several conventional cryptanalysis or classical cryptanalysis for the last 20 years. Okay, but now what we will try to see is that if you implement such kind of algorithms, okay, maybe on some kind of embedded device or maybe on some kind of processor, then there is an accompanying power consumption, right? Because it's a computation that is going on constantly. So if you take a plain text, you get a ciphertext. But it is not only the ciphertext that is revealed to the environment. Okay? So if there is an astute adversary or like a clever adversary, then the adversary will get the ciphertext, but along with it also can capture, say, the like the power traces or maybe the electromagnetic radiations around your device, and then statistically process them. Okay? So now this part, that is the like how the power consumption will get impacted, was not really a part of the design objective, okay, of at least this kind of, at least at that point. So this essentially leads to what are called as side channels, and this is something that we will see how we can utilize. So it turns out often, like the information is leaked because of optimizations. Okay, so let me try to kind of little bit elaborate about what I mean here. Is that suppose, right, you have a code or an algorithm, right, and there you have if-else statements, right? When you write an imperative code, then you have if-else statements in your code. Okay, say I ask you to multiply two numbers. Okay, so what will you do? The first thing probably you will see is that if there is one input which is 0, then immediately you know that the output is 0. If both of them are, both the arguments are non-zero, then you apply some algorithm and give the result. Okay, so now if I give you two inputs and you multiply them and you give me a result which is very fast, okay, and quickly you give me a result and I don't know what is the result, okay, but still I can probably guess that maybe one of those inputs was a trivial input. It could be even 1, for instance, right? One of the input could be a unit input. Then you don't really need to do any computation over there. So in this case, right, this is a very simple example, but this example is essentially telling us that there is some side channel. In this case, that is the timing of the computation. Okay, and the timing of the computation is actually a very, very like hard thing to stop. Okay, even after several years of evolution of developing cryptographic libraries, it is extremely hard to develop a constant time library. Okay, which means that the time in such cases, right, what we expect is that the time doesn't reveal what is the data. Okay, so timing side channels remains one of the classic forms of side channels, and I will try to elaborate, at least in one of the classic papers, how it was exploited. Okay, so therefore, right, often optimizations which are performance oriented conflicts with security. Okay, and it can leak information. Right. So there could be several other examples, and so slowly we will see more examples. So here is a brief history of side channels. Okay, so you can probably take a quick look at this, and I will not go in details, of course, into this. But it turns out that even during World War I's and World War II's, like people did interesting experiments. Okay, which are kind of equivalent to what we call today as side channels. Okay, so apparently in World War II, you can see here, like for example, like Bell Labs were the first to discover that electromagnetic emissions from devices could leak 75% of the plain text that was sent securely from a far away distance. Okay, so this was a classic example of how electromagnetic radiations were used. So likewise, there are several like interesting examples, and I will leave this slide at your disposal. You can probably have a look at these. Okay, but around mid 90s, maybe around 95, 96, there were two very seminal papers from Paul Kocher and their group or collaborators, who came up with probably the first example of side channels, which were which led to this academic study of this discourse. Okay, so these are, I would say, like starting papers where Paul Kocher and their team showed how timing information can be used to break RSA, and they showed how power attacks or power information could be used to compromise RSA keys. Okay, so this would be our logical starting point to understand this subject. Okay, so if I ask you about possible side channels, there are several probably. Okay, so and here are some of them. Like timing, as I mentioned, is the classic side channel. Likewise, there could be power. It could be the electromagnetic radiations. Another one that I will talk about tomorrow is faults. Okay, so imagine that suppose you are doing a computation. Okay, and suppose like the current trips. Okay, and because of the tripping of the current, you get an erroneous output. So what will you think? You will think that, okay, this was an erroneous computation, let me redo the computation and go ahead. But you will be kind of astonished to know that if you take a cipher as strong as AES, if there is one single fault, okay, during the computation, when I say one single fault, the fault is a well-formed fault, and that you will probably understand after tomorrow's discussion, it can reduce the AES key drastically. Okay, it can reduce the AES key from 2 to the power of 128 to only 256 guesses. Okay, and if you get two shots to get faulty outputs, you can uniquely retrieve the key. Okay, so if you can, like maybe when you go home, right, you can do a Google search on a very famous attack which was recently published, which is called as Plunder Volt. Okay, so Plunder Volt is an attack that targeted Intel's SGX machines and showed how somebody like tweaking with the voltage frequency scaling of these computing systems can create faults and faulty cipher texts, and from there get the key. Okay, and you will be also like surprised to know that this was one of the attacks for which Intel had to deprecate SGX from their 11th generation processors. Okay, so they have to now think about a new architecture which is more secure and more like robust against these class of attacks. Okay, so likewise the list can be more. Okay, and I will not get in time probably to talk about testability features. So when you talk about any engineering design, you need to ensure, and when the design becomes more and more complex, you want to ensure that the design is safe, right? You want to ensure that you can test the design. Okay, but you can imagine that when you want a good testing facility, then you want to control and you want to observe. But the attacker also exactly wants that. Okay, and therefore many of these testability features have been actually shown how to break real world crypto. Okay, and I will not probably get time, and if you want to talk, I can talk like offline. So let's talk about this example. So this is my like favorite example because it was probably the first time like that I myself understood what timing side channels is. Okay, so this is a very nice paper by Paul Kocher. You can read this and also try to implement it. Okay, because if you try to implement it, you will understand many nuances. You will know that this is not a magic, this is a statistical experiment. Okay, so it will sometimes work, sometimes will not work, but it will work often with a high probability. Okay, so let me try to explain what it means. So in this case, this particular thing that I show in the slide, so let me see if I can make the pen work. So this particular thing that you see over here is an effort to compute a specific computation which you see often in RSA kind of systems. Okay? So in RSA kind of systems, what do you have? So you have a secret, okay? Yeah, so you have got a secret inside, and let me call this as the key, okay? And when I want to decrypt it, I will probably feed with a cipher, which is y, and it will calculate internally y power of x modulo some n, where n is public, okay? So now as an attacker, what do you want to observe, what do you want to obtain is this x. This x is probably stored inside, okay, a memory. It could be, if you are talking about maybe a credit card or like some kind of embedded device, it could be stored in some non-volatile memory or some kind of secured storage, okay. And now I want to kind of do something to obtain this value of x. So how do you implement y power of x modulo n? So note that if you see the RSA specification or specification of such kind of algorithms, you know that this x is very large. Okay, so this x could be 1024 bit, 2048 bit, and so on. Okay, that means the value of this x, right, can be really, really large. It can be, say, 2 to the power of 1024, of the order of that, right, to the power of 2048. So that rules out a very naive implementation. And what is that? You cannot multiply y x times. Okay, that would be the easiest way to implement it. I will take y and keep on multiplying it x times, but that may require ages, and still I will not see the result in my lifetime. So luckily there is a very nice algorithm that you can get from any standard textbook, maybe from Corman's textbook on algorithms, okay, where you take this x and you write that in a binary format. So what you do is you take x and write down in a binary format. Okay, yeah. So you write down this as, say, xn minus 1, xn minus 2, and so on till x0. This is your binary encoding of x, right? And then you apply an algorithm which is called as a square and multiply algorithm. So what does square and multiply do? So the idea is that you start like reading out this x, say, from the left, and suppose the first time you see a 1 is where xn minus 1 stands, okay, and then the next bit you just try to see whether it's a 0 or 1. So what you do is you always do a squaring, okay, you always take x or whatever your intermediate data and you square that data, but if that exponent bit is 1, you do an additional conditional multiplication. Okay, so if you see, what I mean is this, that is, suppose I want to calculate, say, y power of 7, for instance, then I will encode this 7 as 1, 1, and 1, right? So I will leave out this first one, I will start with the second one. What I will do is I will take y and perform a squaring. Now since this is y, this is 1, I will do an extra multiplication here, okay? So what is this result now? Y cube. So the next bit is again a 1. So I again take y cube, perform a squaring, and then I multiply with y. So I get y power of 7. Right? If this was y power of 5, then I would have written this 5 as 1, 0 and 1. So therefore, since this is 0, I will do a y square, but I will not do the multiplication. Okay? I will not do this multiplication. But therefore, I will see the next bit, and this is a 1. So now I will square and I will multiply with y. So I get y power of 5. Right? Very simple. So this is a standard way of implementing a square and multiply algorithm. But you note that when you have done this implementation, probably that is how I will code in a standard algorithm class. I have used this if statement which I was talking about at the beginning. Okay? But I have done a very big blunder. What I have done is, from the security point of view, in this code I have written an if statement which depends upon the secret bit. Okay? And that essentially is the source of lot of issues, lot of problems. Okay? So let's see what potentially could be, like, or how, at least in this classic paper from Paul Kocher in Crypto in 96, they show to exploit such kind of code. Okay. So is this function clear to all of you? Like, is this clear to all of you? Okay. So now let's see how we can exploit it. So for this, what we will do is we will try to perform, like, let's consider a situation where the attacker has observed, like, say b minus 1 bits. Okay. So what I mean is, I want to observe this xn minus 1 to so far till say x0, but imagine that I know a part of these keys. Okay. So I know b minus 1 keys are already known to me. Okay. And now that means that from x0 to x b minus 2, that is these b minus 1 keys are already known to me as an attacker, suppose. Okay. And I want to obtain the next bit, which I don't know, which is x b minus 1. So this bit can either be 0 or it can be either 1. It can take any of these two possible values. Okay. So if I don't give you any information and I ask you, like, I give you the knowledge of x0 to xb minus 2 and ask you to predict xb minus 1, okay, what will be your best guess? You can just guess randomly, right? Your probability will be half. You will say either 0 or 1, but that can be true with the probability of 1 by 2. But now we will be also observing this side channel of timing and try to see how we can utilize it to increase my probability of guess, okay, my probability of success. So what we do is this. So assume that, so this is where timing measurement comes into the picture. Okay. So I will assume that the attacker has got the capability of very accurately measuring time. Okay. So what the attacker will do is, so if you want to, like, there is a function p, imagine say any function, you should be able to find out very accurately what is the time required to compute this function p. Okay. So for this we will be using, like, any method is okay, but we will be using a specific code snippet, and because we want to measure this timing very, very accurately. Okay. So what we will do is we will compute a timestamp before this function call, and we will measure a timestamp after the function call. Okay. And then measure the difference of these two timestamps. Okay. So therefore if there is a function p, I will have a timestamp here, call it as ts1, okay, and I will have another timestamp here, call it as ts2, and of course, right, the time will be the difference of ts2 and ts1, ts2 minus ts1. So now what I will do is, I will, in order to calculate this timestamp, I will give you this slide so you can play around with this also. This is usually the code that we use often for very accurate timing measurements. Okay. In particular, we use this timestamp counter called RDTSC. Okay. This is a specific timestamp counter which we use to get very accurate measurements of time. Okay. And you will see that there are certain other things also, like CPU ID and so on. There are certain reasons why you use them, largely to, like, ensure that the pipeline is of your processor is always flushed, so that you reduce the, non-determinacy that can come often because of, dependencies and other things in your code execution. Okay. So you can take this code as it is, this code snippet, and you can use it to create these two timestamps, ts1 and ts2, and get the difference of the times. So assuming that you can do this, now what we will do is this. So what we will do is, we will tell the attacker that, okay, now you can, the attacker can observe the timings. So what it will do is, it will take this, like the code which calculates y power of x and feed it with different values of y, say call it as yi, where I can vary over the number of observations. And the attacker, right, will also observe, maybe, like, take some kind of clock and observe this timing required for this yi operation. So it will basically get a list of timings, and I call it as, say, ti. Okay. So every time you are doing this decryption, you are not only getting, not only doing the decryption, but you are also observing the time required in this computation. Okay. So you will have, like, so suppose, like, you are observing the first time as T1, the second will be T2, the third will be T3 and so on. So you will get a statistics of timing. Okay. Now let us try to understand what exactly is really leading to the variations of timing, because you will see that there is variation in the timing. It is not a constant time implementation. So if you observe here, remember that this X, for example, that we had was if you go back to the code, in this case you can see that there is like a for loop that I have, and there is like a kind of an iteration of the code. That means there are certain steps which I am repeating again and again. Okay. So imagine that the ith iteration of this code will take say Ti amount of time. Okay. And therefore, right, if the total length of the exponent is say like some w, for example, that is the width of your exponent, then the total time you can actually calculate or write in this manner as sigma of di, where this I goes from 0 to w minus 1, okay, because that is the total width of your exponent. Okay, your x is of dimension w bits. Okay, does it make sense that how this part comes in? Okay, so it's just like I'm just writing symbolically that every iteration takes Ti amount of time, and this goes on from 0 to w minus 1. Now there is an additional term that I add here, E, and that I add to accommodate the various kind of errors that can occur during the computation. It could be measurement error, it could be the various kinds of inaccuracies and so on. So it will be roughly the sigma of Ti plus some error. Okay. This is the time that is required for doing say the jth decryption. Okay. And therefore I denote it as with some Tj variable. So that means say I am doing the first time I am doing it, I am doing the decryption with input y1, my time is T1. Second time I am doing say y2, the time is T2, and so on. The jth time I am doing, the time is Tj, and so on. This is the statistics that I am accumulating as an adversary. Right? So now note that what I said initially is that the attacker knows partially this key, that means the attacker knows till b minus 1 bits and wants to obtain the next bit. This bit is unknown. Right? So what I now can do is I can create a code which is like a replica of this code, where I can fix these values from 0 to b minus 2, and this extra bit is something that I can guess in my own code. Okay. So what I do is I write this loop, okay, again in my own, in another function, and these functions the bits I vary from x0 to xb minus 2, and the last bit is something which I don't know, xb minus 1, it can be either 0 or it can be 1. Okay. And I create another sort of a replica of this code, and I also measure the time required to do that. So now therefore if I create this replica, so let me write down this replica code. This replica code will also take will take different amount of timings, and I call them say with these small timings as a T1 star, T2 star, and so on till Tj star. Okay. So this essentially, so these start timings essentially correspond to computing from x0 to xb minus 2 and xb minus 1 being guessed. Okay. So this guess is either 0 or this guess is either 1. Okay. It can be either 0 or 1. And now I calculate the difference of these two timings. Okay. So if you calculate the difference of these two timings, then you will see that in the first time you have got this particular term which I explained, and in the second part you have this where the loop index goes from 0 to b minus 1, because this is the case, this is the situation where you are computing the timing for your replica code. Okay. And your replica code goes from x0 to xb minus 2. All of these are known to you. You know what is the exact key in those cases. xb minus 2 or xb minus 1 you don't know, so you make a guess here. This guess could be either 0 or it could be either 1. Okay. And now if you calculate the difference of these two timings, you note that, just pay an attention here, you will see that from 0 to b minus 2 are exactly the same as your target code, right? Because I had guessed that, I had assumed at the beginning that from 0 to b minus 2 are those key bits which you know, which you already know, okay? And therefore, if you calculate the difference, from 0 to b minus 2 will get cancelled out, okay? Because you know that the execution will exactly match with that of the attacker. Because in this case, when you are processing x0, if your code has 0, the attacker's code also has 0. Okay? If your code has 1, the attacker's code also has 1. And why will it match? Why will the timing match? Because in this case, the additional multiplication that I mentioned is happening only when you have a 1, will either occur in your case and also in the attacker's case, or will not occur in your case and will also not occur in the attacker's case. So the timings will be almost identical, except some error and noise and other things actually. Okay? So statistically they will be the same or similar. So the only difference that can probably come is because of this b minus 1, because this one I don't know, this one I have guessed. Okay? And therefore you will get this additional delta term which essentially is difficult to predict. Right? So you will see that the difference of these two timings, like if I say, like Tj minus Tj star as I was mentioning and call this as say Tr, will essentially have, of course, this error plus this difference of timing, and the remaining other parts I don't know. They are from b to w minus I. Okay? Why? Because in my replica code I had only from 0 to b minus 2, but in the attacker's code it has x0 to x w minus 1. So these are additional timings which will also be there. Okay? So therefore in the difference you will have this term and also this term, both of them will be there. So now note, I mean in Coach's attack what they observed is that if you are able to, so now if you take this TR, okay, and you are seeing that you are observing this TR and you are doing it for all the possible decryptions that you are doing, you are getting a statistics. Okay? And now if you calculate the variance of these statistics, then you will see that because of the fact that in the correct case, that if you are guessing the key correctly, then this term will go to 0. Okay? Why? Because you have guessed exactly as that of the attacker. Okay? But on the contrary, if you have not done that, then that term will actually increase or contribute to your variance. So you will have got more disturbances and the variance will increase. So therefore now what you do is you basically calculate this TR, so you have a statistics of TR and you try to find out what is the variance of this TR. Okay? Now note that this variance of TR is dependent upon two guesses. So this guess could be either 0 or this guess could be either 1. So you basically compare the variance of TR for the guess 0 and the variance of TR for the guess 1 and try to see that whether the variance increases or decreases. Okay? If the variance increases, that means this variance is larger than this one, then you know, because you know that in the situation where you have correctly guessed, the variance is smaller. Okay? So therefore if you have a situation like this, then what should be your guess? Should it be 0 or should it be 1? It should be 1, right? Because when you have guessed it as 1, then the variance has diminished. So you are more certain. Okay? So therefore, like what you will do is probably you will vote for 1 in this case. But again, as I mentioned, this is a statistical attack, so you have to do it over a large number of observations and see whether majority is voting towards 1 or whether majority is voting towards 0. Okay? And that way you can recover the b minus 1th bit. So note that now this is an iterative attack. So you first don't know anything, you recover the first bit, then using the first bit you recover the second bit, using the first bit and the second bit you recover the third bit, and so on. Okay? So like intuitively, what do you think should be the complexity of this attack? If you have an n length decryption exponent, right? Well, I mean, I would rather say order n, because you are requiring n number of efforts to recover, like I'm just talking about So when you do this kind of analysis, right, you just focus on how many iterations you need to do. Okay, so every time you are recovering one bit of the exponent. So the first time you get the first exponent bit. Second time using the first, you get the second exponent bit. Then you get the third exponent bit, fourth, fifth, and so on. So this is linearly proportional with the length of the exponent. So it's very efficient, because even if I increase the length from 1024 bits to say 2048 bits, it just makes the attack a little bit more complex, but doesn't scale up exponentially. Okay? And that is why it can be devastating. Note that we have not tried to do any complicated mathematics, like not really solve the factorization problem or anything of that matter, but you can, if there is such kind of vulnerability, you can very easily leak the key. Okay? So till this point, are you with me? Till this point, any questions, comments? So I will request you to, go back and have a look at this paper if you are interested actually, okay. So this is a very nice paper, you can have a look, it's freely available now, just Google it out, you will get it actually, okay. Okay. So there are very interesting extensions of this into other variants also, like defilement, probably you have studied defilement in the course, right. So you can also take a look at them. Okay, so any questions till this point? So do you get the idea, right, how timing attacks work in general? Okay, so now let's try to see a slightly different, attack vector, and this is where I will talk about power side channels actually. Okay. So timing still remains one of the most common forms of side channel analysis. Still now people publish papers and research on timing side channels. But for the sake of time, I will move into another form of side channel, which is also very popular, which is called as power side channels. Okay. So it requires a bit of experiments, but in our class or discussion we will be agnostic of that. But it's good to probably understand on the hindsight how an experimental setup should look like, and it's not very fancy. Okay. So what you have, yeah.
In the previous part, when the size of the when we got 10 bits and we are doing for 10 plus 1, then the time is not order n for that, for the computation, we are summing over from B to W.
Yeah, so this kind of analysis, you assume that every iteration what you are doing it in constant time. Okay, that is order 1 time. Okay, so what I am just trying to find out is how many iterations you need to get the entire key. Yeah? N iterations, and yeah, so that's why I said order n actually. So what I just mean to say is that your complexity of the attack is linear with the length of them. Okay, if I increase it from 1024 bit to 2048, it will probably become a little bit double than complexity, but not exponentially large. Okay, so let's take a look at power side channels. So in power side channels, the idea is that you have some kind of device. It could be your mobile device or maybe your credit card. All of us are carrying credit cards. You will see, I don't know how many of you have seen that in the credit card there is a small chip, right? You have seen that there is a small IC, right? That's a chip. So it's usually our credit cards nowadays follow a principle which is called as chip and pin. Okay, and you will see that inside that chip and pin, right, there is also very nice crypto going on. Okay, that motivates us to study cryptography actually. Okay, so now you will see that if there is, for example, some kind of crypto engine which is running over there, okay, and when it is performing its operation, you are suppose curious to know what is the power consumption during that computation. Okay, so here you can, this is a kind of very classic setup that you can see here, which we have in our lab. So we have an oscilloscope, we have a PC which controls and synchronizes the communications, and there is a device under test. Okay, so this is the device under test. So here you can have your credit card, you can have an FPGA device or an ASIC design, where these are the various cryptos that can run. It could be a DES chip, a 3DS chip, or an AES chip. It could be an RSA chip, it could be an elliptic curve system, whatever, right? So it could be some target crypto that is executing on this device. And now what I do is, from the PC, I send input for this to either encrypt or decrypt, and when it is doing its computation, I have got some kind of probe. Okay, so these are called as probes, which measures the power consumption and stores in some oscilloscope. Okay, and this oscilloscope synchronized with the PC sends this data to the PC. So therefore, at the end of this experiment, what does the PC have? The PC has plain texts, it has got cipher text, but also it has got the corresponding power traces. Okay, so it will probably look like something like this. This is the power trace for the first encryption. Okay, you again do another encryption, this is another trace that you observe. So it could be a collection of observations that you essentially make. So here are some snapshots. So here is some of one of the devices that we have. This is the target device on which you are measuring, and so on. So I will show you some more pictures. Okay, so largely, again, by this great paper from Paul Kocher and team in Crypto 99, they came up with this idea of what is called as differential power analysis, which I will elaborate in our discussion. But largely, power attacks or sidechain attacks falls into two categories. Okay, the first one is called as simple power analysis or SPA, and the second one is called as differential power analysis. So what is simple power analysis? So simple power analysis means it's a power analysis which exploits the fact that power consumption depends upon the underlying operation. Okay, so remember this square and multiply algorithm that I mentioned. Okay, so there were two primitive operations. What were the two sub operations that you were doing in that computation? Square and multiply, right? So you were doing a square and you were doing a multiply. Now suppose the power consumption of the operation square and the power consumption of the operation multiply are different. Okay, then if you can do an attack, then this attack is called as simple power attack, because you are exploiting the fact that the power consumption of the operations are different. Now there is an even more devastating attack which is called as differential power attacks, where you exploit the fact that power consumption depends upon underlying data. Okay, so the reason why I say it is more devastating is you can actually defend against simple power attacks in a very naive manner. What you can do is, although you are doing this multiplication in a, sometimes you can do an implementation where you always do a dummy multiplication. Okay, whatever be the exponent bit, let me do an extra multiplication. That's a bad implementation, but still it should prevent against these class of attacks, right? Because you are always doing both squaring and multiplication, right? But interestingly, you cannot prevent against what are called as differential power attacks, because differential power attacks exploit the fact that power consumption depends upon the internal data. Okay, and that essentially comes from the underlying device physics and so on. Okay, because you will see that most devices on which your entire hardware and whatever, like eventually you are doing your computations on some hardware device, right? So it's a bunch of transistors which are turning on and turning off. So they are turning on and turning off times or power consumptions are not same. Okay, and that is a fundamental reason why it will always leak, because of this asymmetry of 0 to 1 and 1 to 0 transitions. Okay, so that means like if I can observe this power and understand the manifestation of this from on the actual data, then I can get intermediate data, and that can be devastating. Okay, so think about the AES algorithm. In the AES algorithm or the AES 128 algorithm, you have been given some specifications. Okay, what is the specification? You take a 128-bit plain text, you take a 128-bit cipher text, 128-bit key, and you allow and you perform 10 rounds of operation. Right? Certain operations are already specified, and then I give you the cipher, and then I give you a reasonable level of confidence. Okay, But now using these kind of techniques, if you are able to observe the intermediate data after say the first round, right, then the mathematical guarantees go for a toss because they were not designed for those objectives, right. And that is where, like, although you have made a nice lock for your house, but the attacker can get through the, like the easier path. Okay. So therefore, right, you need to also factor in such kind of issues when you want to really implement and deploy your crypto systems. Okay. So luckily, all the credit cards that you are carrying in your pocket have got protection against such kind of attacks. Okay. Luckily for us. So let's see how a power trace would look like. So in a simple power attack, okay, so let's talk about AES for instance, okay, and this is the reason why I am talking about AES is because it is still one of the most commonly occurring block ciphers. Okay, so let's we take, so we will use certain terms. So one of the terms that I will be using again and again is traces. Okay, so traces means it's a set of power consumptions across a cryptographic process. So, but then like the power consumption is an analog process and it's a continuous process. But when I want to kind of do my algorithms that we will see soon, you will be working with zeros and ones. So you need to discretize this. Okay, and how do you discretize this? By sampling this power trace. So you take the power trace and you have an oscilloscope which has a very high sampling rate. Okay, and you want to have a high sampling rate because you don't want to miss information. Okay, and then so if you have got, say in this case I show you like 1 millisecond operation sampled at 5 megahertz will yield a trace with say 5000 data points. Okay, that means although you are doing say one encryption, this encryption will have like 5000 points. So this is just like give you some numbers, but this can vary. So in the trace there will be 5000 time instances when you are observing the power value. This is a real power value, like something. So when you observe the power consumption, often what we do is we have a probe. Remember I showed you this diagram where you have a probe and you try to measure say the current consumption. Okay, so the current will be in something like in ampere or so on actually. Okay. So like that, like you observe this power consumption and you kind of have a plot. So this will probably look like this. Okay, so maybe you can, just to give an example, this is a power trace of AES. Okay, and you can see here that this is a power trace of AES 128. So already you can see certain things in this trace. Can you tell me what can you see from this trace and infer back at the AES algorithm? So AES 128, I told you something, right, that it has got 10 rounds of operation. So can you see those 10 rounds in the power trace? So if you count, so there are 10 jumps, very periodic, right? So you can practically read and note that like when I am observing this power trace, I am doing this power trace from the voltage line actually, or the point where it like supplies to your entire board. Okay, so it is not only the crypto that is running, but along with it there are several other things also running. But still you are able to kind of do certain, like if you are properly observing the trace, then you can essentially get such a nice trace where you can essentially see all the jumps in the 10 rounds. So you can see identical, like operations, all these 10 rounds are pretty identical. Okay, sometimes these traces are so nice, sometimes they are not so nice, but I am like showing you a very nice situation at this point. Okay, so now the question is, right, you are getting variations, but can you exploit these variations? If you can exploit these variations just by seeing this trace, if you can tell me what is the key, then that is an example of simple power attack. Okay, but most likely you will not be able to do that in case of AES, and you need more complicated techniques, which brings us to what is called as differential power attacks or DPA. Okay, so there you need more statistical techniques because you need to exploit the fact that the power consumption depends upon underlying data. So in order to understand that, you can zoom in into maybe one of these rounds and try to see what is happening over there, and here is a zoomed in version. Okay, so you can see here, this is inside the round, you can see like different kind of power traces, signatures. So typically, right, if you know how the AES works, in the AES, the first part in the round of AES, there are some sub boxes or like S boxes, which I will probably talk a little bit in my discussion. Okay, so this part is typically corresponding to the S boxes, and these parts are typically corresponding to some other operations. Okay, So you can very distinctly observe the differences and see the sub operations as well. So now what we would like to do is, we would like to see like how to get the actual like AES code. Or what I will do is, I will, after this break, I will start to talk about the AES algorithm, and then later on talk about how to do a power attack on AES. Okay, so so this was this particular thing was taken from a specific board which is called as Sakura. Okay, so Sakura is a Japanese board. So you can actually so these were at that time when we did those experiments. Initially they used to give us the boards free, but now they don't give it free, so you have to pay some money, and then you can get those boards. The other place where if you're interested you can work with them is, there are these boards which are called as Nexus boards, NEXYS, Nexus boards. These are very cheap or reasonably cheap FPGA boards. Okay, so yeah, I think it costs something like 15,000 rupees, 16,000 rupees, and comes with a nice pack, like in a package and things like that. Nice for students to carry also. Okay, so you can work on them. Yeah, so for those who like simulations, okay, and understand, but I'm not undermining that actually, because many of these techniques, right, you can actually, once you understand what to simulate, you can actually simulate them and create nice techniques. Okay, and you can actually do a lot of statistical processings and so on. Like nowadays people like write a lot of papers of exploring machine learning techniques for side channels. Okay, so many of these are based on like test benches and benchmarks. So you will see in the literature, I will talk probably at the end, give you some example names of benchmarks which you can download from the internet also, and you will get a lot of power consumption traces and things like that. Now if you have a better method, you can try your method on them. Okay, so this is a pure simulation that you can do and validate it on those benchmarks. Okay, so in one of at the end, right, I mean Siddhartha is with me, so he is a senior PhD student. So what he will show to you is some codes which we will offer you. You can take those codes with you and you can just play and plug with them.